Yeah, so this is the plan of my talk. I want to first we'll do some kind of conceptual, kind of semi-technical discussion, but I will try to keep the mathematics low. So for those of you who kind of have mathematical relativity standards of precision, you would be very unhappy with this talk. But I hope in this way it will be kind of more accessible to all of us, because I understand that you have very different background. Some of you have background in physics, some of you have background in philosophy, all sorts of things. So I hope this will strike the right balance, but probably what's going to happen is that everyone will be unhappy. But that's just life. Okay, so I want to spend, roughly speaking, the first half of the talk kind of having a sort of framing kind of discussion about how to approach the issue of determinism in general relativity. And then, so this will have nothing to do with dark energy. But the second half will be about what happens in cosmological models with positive cosmological constant and what happens to black hole spacetimes with positive cosmological constant. So no dark energy in here, a lot of dark energy in here. That's the plan. All right. So yeah, so let's have some kind of initial framing sort of discussion. And I think it's proper to start with, sorry, can I get rid of this blue thing? No, I shouldn't. It distracts me, but it's all right. So yeah, I would like to start with a sort of general discussion of determinism in physical theories. So here's what I think is a kind of standard and very common sense approach to what determinism is about. Sometimes it goes under the name Laplacian determinism, and this definition, I think this exact framing may be not there in Ehrman's 1986 book on primer on determinism, but spiritually it's sort of all in there. So we say that a theory T is deterministic just in case, given the state description at any time T1 whatsoever, the state description at any other time, to the future or to the past, is in principle deducible from the loss of the theory. And of course, this question could be asked about all sorts of physical theories, right? For instance, we could ask, well, is classical mechanics deterministic? And then, as some of you may know, the somewhat surprising answer is, well, maybe not. We have all sorts of examples, such as space invaders, infinite collisions, funky geometrical shapes, such as Norton's dome, and so on. And we could also ask this question about quantum mechanics or quantum field theory, or basically any physical, or not only physical, also biological or sociological or whatever scientific theories whatsoever. And kind of, we could also ask this question about our universe and physical subsystems within it, as insofar as those subsystems are represented by some physical theory, right? And this may seem like a split-in-hair kind of distinction, but we could imagine a situation in which, let's say, some quantum field theories are indeterministic in some strong sense, but the standard model of particle physics turns out to be deterministic in the same sense. So those are logically very different questions, I think. All right, and as promised, I want to talk about general relativity, and insofar as cosmological constant is concerned, also cosmology with dark energy. And the first thing to be said about GR is that this very intuitive and plausible idea of determinism instantly, if you excuse that horrible pun, runs into serious troubles. Okay, so why is that the case? I will frame it in sort of in the context of what is sometimes facetiously called in the literature the Church of the Angles brackets. And I just realized that I'm not really using the angle brackets for the ordered pair. I'm just using the standard. kind of rounded brackets notation, so please substitute whenever. So one, I think, very common in the philosophy of space-time literature view on what GR is that it's about relativistic spacetimes. So what are relativistic spacetimes? Well, it's a class of objects which basically consists of sort of, you can have different presentations of this, but for simplicity, we can think of those as a manifold and a Lorentzian metric. Okay? So we're interested in understanding the structure of the kind of like following class of objects. We want to have some kind of a space-time manifold, which we think of as a collection of point events. And the manifold should satisfy some conditions, should be, well, n-dimensional, should be connected, right? We don't want to have one piece of space-time here and another disconnected far away from here. That sort of doesn't seem physically plausible. It's commonly assumed that the manifold is smooth, so we can talk about, not only about the topology of the manifold, but also about class of continuous, once differentiable, twice differentiable, n times differentiable, and so on, functions over that manifold. And that's great, because then we can talk about, also tangent spaces, tensors, geometric objects defined on it, and so on. And a lot of this you sort of implicitly have seen in Eric's talk yesterday already. And there are some further constraints that some philosophers object to, like the fact that manifold should be Hausdorff, but I will not get into it today. And so this is like the first pair of this order, the first element of this ordered pair. And on top of this, we have a Lorentzian metric G. So we have a kind of like familiar relativistic signature, let's say minus plus plus plus, or well, n times plus, if you wish. And we think that this metric that encodes curvature and distance relations, and also chronological and causal relationships inside the spacetime, is related to some source term T through the Einstein's field equations, which you have also seen in Eric's talk yesterday. And just for simplicity, I'm just working with the Lorentzian metric G because we can always use Einstein's field equations as a definition of some source term T. Okay, there are some caveats. The first is that in a kind of like mathematically proper presentation, you would see like a little like tensor indices. So G would be like G mu nu or GAB, and similarly for T mu nu. And I'm dropping this throughout the talk because we will not need them, but sort of they're there implicitly. The second caveat is that, well, I think it's a very kind of like formally elegant way of looking at general relativity, but it's limited. For example, arguably, we cannot really represent black hole collisions of the sort that we have observed with LIGO, Virgo, Cagra array in these terms, because no one knows how to write a smooth metric for a binary black hole merger. The way we model that is through numerical relativity, which uses a lot of discretized approximations, and we just don't know what would be the right smooth Lorentzian metric describing something like the crucial part of a black hole merger, so the moment where two black holes collide. So this framework has all kinds of limitations. And another limitation that may be a bit important later on is this requirement of smoothness, because it will turn out that in the context we will be interested in the very last part of this talk, will be dropping that requirement to some extent. All right. So the next thing to talk about is it's the definition of determinism, right? The Laplacian definition I showed you. So in that definition, we're asking about something like state of the system at a moment of time, and we're trying to deduce state of the system at any other moment of time. But, well, what are moments of time if we take this view in general relativity? If we're just considered with any manifold that meets the nice enough Lorentzian metric, and plenty of them will not have anything like our kind of like commonsensical notion of time. For example, in what I think is the best birthday gift anyone could ever give to someone, Kurt Gödel presented to Albert Einstein his cosmological solution, and that solution has a closed time-like curve going through every point. So, we're sort of meeting here and now, and, we're traveling, everywhere towards the future. And yet, at some point, if we, move on certain kinds of trajectories, we end up being in exact same space-time location as the one we're here now. That can happen in general relativity. That actually happens in some of the black hole solutions, and there's plenty of spacetimes with this property. And so how do we even think about something like notion of moment of time or state of the system at a moment of time if we're faced with such a solution of the Einstein field equations? So in more precise terms, something like moments of time, which might be kind of like a good way to set up even the question of determinism, would be to ask about something that relativists call a Cauchy hypersurface. So a Cauchy hypersurface is like n-1 submanifold, which you can think of as, if this would be something like a Minkowski spacetime, then we fix some space-like hypersurface. And in Minkowski spacetime, of course, there's kind of like the choice of the hypersurface is highly non-unique, and this will also be the case generically in other relativistic spacetimes. And that's a philosophical discussion about the whole argument and diffeomorphism invariance and so on that I want to get into today. But basically, I will invoke a theorem, I think, on the next slide that kind of tells me it doesn't really matter what our choice of the hypersurface is. Anyway, Cauchy hypersurface is a submanifold such that it is intersected exactly once by every inextendable causal curve in M. So how to think about it? Well, maybe, this is my spacetime manifold, and it could happen, it will have all kinds of smooth curves going through, and the Lorentzian metric will induce something like a light cone structure, right? Sometimes the future light cone will be wider, sometimes it could be narrower, sometimes it could be exactly like in the Minkowski spacetime. Here it gets very wide. And so we take every such curve, which is kind of like as large as it could be, and if we can find some sort of slice, like this one, intersected exactly once, but every of those curves, then we say that the spacetime has a Cauchy surface. And I will not do that because I think the University of Urbino would not be very happy with me if I did that. But if we took this whiteboard and kind of like identified this edge with this edge, then certainly we could find what would happen after such an identification, after we rolled up the whiteboard, would be that this spacetime would no longer satisfy the Cauchy property, right? Because it would be kind of like periodically identified, and therefore any choice of the surface would be intersected multiple times with such curves. Okay, now what happens in general relativity is that there is, this is just one of what relativists call the causal hierarchy of spacetimes. And so I will not go into the details of this. The takeaway about this is that this condition that there is a Cauchy hypersurface in spacetime is equivalent to this condition here, called global hyperbolicity. And we can find plenty of examples of spacetimes that do not have this property. In other words, they do not have Cauchy surfaces. And like all of those implications are strict, so we can find the causally simple space and that's not globally hyperbolic, continuous, that's not simple, and so on and so on. And so what this means for us is that when we want to understand the question, is determinism true or false in GR, and we start with this intuitive idea of Laplacian determinism, well, it kind of like depends on how strict we are. We have this rich causal structure and we have a lot of freedom in constructing various relativistic spacetimes. I will use that freedom in my second talk on Thursday to do some wild stuff. That simply because of this freedom that we have, and again from this kind of like interpretational point of view, with this interpretational framework I have in mind where we're looking at the set of Lorentzian spacetimes, it's very easy to produce plenty of failures of determinism. For instance, even from this spacetime, right, it has a Cauchy surface, but maybe I'll take, Eric is not here, so let's, Eric has been removed for today by unfortunate circumstances, so maybe we'll take Eric-like shape in the spacetime and remove that subset of the spacetime manifold and maybe do some further tricks with it. And so you will instantly see that there will be plenty of causal curves that sort of like hit the locations where Eric used to be, which are inextendable. We cannot smoothly extend them simply because this region is gone and they no longer intersect this hypersurface sigma, so it's not Cauchy. So all sorts of things can kind of like emerge out of the Eric-like missing shape in here. Of course, this is like a very silly example. There's nothing physical about this. But these sorts of, like a more physically motivated versions of this could happen. For instance, if you have gravitational collapse resulting in naked singularity, something not that different from this sort of situation occurs. Okay, I think this leads to all sorts of deep interpretational question about what to even think about the theory, which allows for, these sorts of things, and I'm very happy to talk about this over coffee or drinks. But let's go back to the question of determinism. So it turns out that if we are in a spacetime with a Cauchy hypersurface, oh, I see that you guys are like taking photos of this constantly, but Nicola or Marco, should we just like upload our slides at some point later? Yeah, Nicola already has my slides, so let's just put them on the website or something. I will be drawing some things throughout, so those are not on the slides, but apart from that, don't bother. All right, so when we're in this fortunate situation that we're considering a Lorentzian spacetime with a Cauchy hypersurface, we have an important and deep theorem going back to Yvonne Choquet-Bruhat and Bob Garrosh from 1969, which states that if you consider this sort of object, a Cauchy hypersurface, and you endow it with geometric data about curvature and about matter fields and about how it's supposed to be embedded in the resulting spacetime, then for a number of specifications of matter, we can prove that the Einstein's equations uniquely determine what happens in the very domain of dependence. So what is domain of dependence? Domain of dependence for some hypersurface sigma, and maybe it's not as large as it could be, maybe it would be extended, but it's the set of all points such that no matter which curve, causal curve, so time-like or null, right? So like a trajectory of either massive particle and accelerated observer, whatever, or a trajectory of a photon, if all of those curves, if we propagate them far enough backward in time, will intersect with sigma, then this point P is in the domain of dependence of this set. And so if this would be something like a Minkowski spacetime, then we would just get like a familiar light cone structure over this set. And if it's the whole Minkowski spacetime, then we're just getting the whole spacetime, which is great. But of course, in general, we'll have varying distribution of curvature and matter, and the relationship is encoded in the horrible Einstein equations. So the shape of this can look very different in general. Yeah, so the theorem is great news, right? Because if you have a Cauchy surface, then within the domain of dependence of this object, we have existence and uniqueness of solutions to a large variety, not all, but large variety of the source term. So in that sense, you may think, oh, general relativity is deterministic, right? Well, but wait. It's only deterministic if I have this Cauchy surface, and it would make sense to have a Cauchy surface because it's like a sensible notion of time at an instant, right? But this sort of seems to trivialize the problem, because if we make it precise what the moments of time are by invoking Cauchy surfaces, then we seem to trivialize the whole problem, right? Because explication of an assumption of a definition, what is a state of the system at a moment of time, well, it's something defined on a Cauchy surface, automatically rules out all sorts of spacetimes, in particular, like everything down here on the causal ladder. So that's not great, right? It seems that this definition of determinism is sort of circular. Not great. Okay, so there are ways around this. Maybe you could say, oh, maybe I could require a different causal condition, or maybe I could do some funky interpretational moves. There's interesting, I think, not just because I wrote papers on this, but generally interesting philosophy literature on this by people like Chris Smink and Chris Wuttrich, and of course, going back farther, John Ehrman and numerous others. But those are sort of some of the conceptual problems when we try to think about determinism in GR. So now, for the rest of the talk, we'll try to think of the situation in the following way. We think of, a dynamic system that is sort of like initially defined on something like this. And in virtue of the Choquet-Bruhat and Garage theorem, we will know that it has, so we're sort of like considering this kind of situation. Now, here is our slice sigma, and in virtue of the Choquet-Bruhat and Garage theorem, we know that this entity will exist. And now we will ask about the properties of that object. So in particular, one natural thing to ask is, in the Minkowski spacetime, we know what happens, right? Every causal curve is geodesic. Every geodesic time-like renewal is complete, right? None of them kind of like, drop abruptly by, let's say, by running into Eric shape. Okay, so we know that this object, the development of the initial data on that exists, and now we're asking the question, well, is that object as big as it could be? And in Minkowski spacetime, it is, and in some other spacetimes, it also is. But generically, like, could we find a slightly larger, let's say this is our, M1, G1, could we find some larger spacetime M2, G2, such that this object is embedded as a proper subset into this bigger object? Generically, in GR, we should expect that, for kind of like generic initial data set, the development of that will not be complete in virtue of the singularity theorems that apply to black hole formation and to some cosmological situations. So we know that is kind of like, as far as classical GR is concerned, that is sort of like of the out of the algebra of possibilities, so to speak. But we can still ask, well, maybe those data sets, even if they're incomplete, they're kind of like incomplete in such a way that we cannot add anything more to them, right? That happens in, let's say, the space-times with a Big Bang type singularity, unless we do some additional kind of like physical tricks, let's say violate some of the assumptions that go into the theorems, violate energy conditions. We cannot add anything to the past of a GR spacetime. Of course, we can do that in some quantum gravity models, but those violate the assumptions of the theorems. So everything is good on that front. But it could also happen that, you know, if this is our cosmological model and we propagate it into the past, there will be sort of singular bits to which we cannot extend the spacetime, but there may also be non-singular ones through which the spacetime could be extended. And if that happens, we say that the globally hyperbolic development is extendable because we can find a bigger spacetime into which it can be embedded. And this boundary we call Cauchy horizon. Okay, and why am I talking about this? Well, first of all, because if this situation occurs, then generically we can find many inequivalent extensions through the Cauchy horizon. So determinism fails in the sense that this region here could have come from very different sort of past in a way, or it could be continued to the future in multiple different ways. And the second reason why we're interested in this is because we do see this phenomenon in some in some black hole spacetimes, and dark energy sort of changes our assessment as to what happens in those black hole spacetimes. Okay, and I think the last sort of like bit that I need to set up what will happen later on is to sort of, so where are we so far? We know that, you know, under some conditions, this object globally hyperbolic development exists and is unique. And now we're interested in the question of, you know, can it be further extended or not? And that, turns out that there are some explicit models in which this can happen. The rotating black hole spacetime, the curved spacetime is, for instance, one of them. And now we want to know what to think about this. If we think of this as, you know, some sort of investigation about whether determinism is true or false, and if there are either our universe is described by a cosmological model that can be extended through a Big Bang, or maybe there are subsystems which are Kerr-like, which are like rotating black holes. And after all, we do expect that every single isolated black hole in our universe is essentially Kerr. So it's essentially that. So it seems that all of this kind of abstract-looking nonsense, maybe to some of you, is actually important if we want to understand the question not only whether GR as a theory is deterministic, but also whether our universe, insofar as it's described by general relativity, is deterministic. And I told you that there are some exact solutions that can be like explicitly written down that contain these things, Cauchy horizons. And now I want to talk about a kind of expectation that some theoretical physicists have. So the expectation is that, you know, despite all of these complications, at least if we can set up GR or Einstein's field equations as this sort of dynamical system, then these situations where you know, Cauchy horizon forms, determinism fails, and we can extend spacetime in multiple different ways, and all kinds of crazy stuff happens. The expectation that some theoretical physicists have is that those are rare situations. Those are non-generic. Those are, you know, unstable against some kind of perturbations. But generically, we should expect that this thing is all there is. So in other words, if we like made some small perturbation epsilon to this initial data set, then these bits would not have Cauchy horizons anymore. That's the sort of thing we'll now kind of like look at. And so this expectation is phrased by what is sometimes called strong cosmic censorship conjecture, or I think it really should be called conjectures, because we should invest, well, why in a moment. So the expectation is that for generic, oh, and I phrased it so that we sort of like, the italicized version will be kind of like philosophically worrying questions, but what is here is what is sort of a theoretical expectation, so to speak. So the expectation is that for generic, and a philosopher could ask, but in what sense? What does it mean? Initial data, so initial data defined on a Cauchy hypersurface, and of course we should say, well, initial data satisfying a bunch of further conditions. Maybe they're compact, maybe they're asymptotically flat, maybe we should also say something about the source term or energy conditions. And again, Eric mentioned a lot of these things in his talk yesterday. Their maximal globally hyperbolic developments are inextendable. And you could also ask, well, in what continuity class? Yeah. So this is the statement of the conjecture. So it sort of tells you, once I have a system that's kind of like nice enough, and I develop I evolve the system in accordance with the Einstein's equations, then generically, only the good, safe part that I can control through the interventions on this initial data set will be what's out there. And all of those kind of like highly non-unique extensions will not arise generically. So that's already, you know, if you think of determinism as a sort of like, is there a solution in the following way? Is there a solution which is specified at some time t, but then for you know, it has kind of like, it could be embedded into two different spacetimes in equivalent ways. That question is already resolved, right? Like already the Kerr spacetime resolves that question. And so in that sense, we have like a very clear answer to whether GR is indeterministic or not. It's not. But now we want to have kind of like more control over it, and we can, which is why physicists add this sort of like statement about genericity. It's a sort of like, you know, as a theoretical physicist, you've already lost a battle, right? A form of non-uniqueness arises in GR, but now maybe the form of non-uniqueness is kind of rare, is kind of unstable, is kind of like non-generic, is kind of, the violation of determinism is highly fine-tuned. Yeah. Okay, all right. So I want to summarize what happened so far. So we looked at GR seen as a collection of all Lorentzian manifolds. And then I tried to convince you that it's very, very easy to find examples of indeterminism. And this, what I think is a deep philosophical question about which of them are physically reasonable or physically sensible arises. And we then looked at the globally hyperbolic developments of some initial data sets. And there we're kind of in a slightly desperate situation, and we equate determinism with the validity of some form of strong cosmic censorship. And now what I want to do in the rest of this talk is think about what statements about determinism could be made about our universe or subsystems within our universe as considered in the context of dark energy. And I will only look at two scales, cosmological spacetimes and black hole spacetimes with cosmological asymptotics. So this is far from a complete story, right? There's nothing about structure formation. There's nothing about galaxy dynamics. Like all of this messy but very real astrophysics is kind of like out of the picture here. And kind of like tying back to a lot of things that Vera discussed, I will mostly just think of dark energy as simply a positive cosmological constant that is like a fixed value. There's no time varying cosmological constant. It's like kind of like further unexplained, and or kind of like, you know, there's no kind of like complicated dark sector with its own kind of like dark particle physics. None of that. All right. So now, now I'm kind of like halfway through the talk.
Sorry, Juliusz, can you remember to me is acrostic MGHD is the meaning?
It's this globally hyperbolic development.
Okay.
So yeah, so formally speaking, we would say
So M is manifold?
M is maximal. So it's but maximal here means maximal as a globally hyperbolic development.
Maximal, global,
Right.
hyperbolic.
Development. So this is the thing that Choquet-Bruhat and Garrosh theorem tells you. That we sort of have to prove that separately for each source term, of course, but for a large variety of them, this thing exists.
Is it the analogous of the normal diamond of Minkowski spacetime in the general?
Yes. Right. Yeah, yeah. Because if we were now, let's, you know, why the maximal bit is there, right? So imagine we're now dealing with Minkowski. We have some slice sigma, and you know, like we could have, you know, this is some evolution of the data over there. But it's kind of like with my example of Eric over there. It's a sort of, it's not as large as it could be in the sense that nothing about the physics specified on this slice sigma prevents it from being a bit bigger, right? So it's maximal in the sense that it's the largest of those developments. And maybe I'll just add one digression about this, which is that for those of you who are kind of like more logically minded, there's an interesting subtlety here, because the way that Choquet-Bruhat and Garrosh proved this theorem in 1969 is that for the uniqueness of the maximal development, they had to rely on the axiom of choice. But that has been since relaxed by Jan Spierski, and I think we can be just proven with a countable choice now. And since some of you seem to be at least amused by this, I would like to add that there is a number of sort of like statements in the study of global spacetime structure. For instance, that the statement that every spacetime has an inextendible extension, not necessarily globally hyperbolic, and the only proofs of this that I know also rely on axiom of choice, and it would be great to know if that assumption can be relaxed, be kind of like more constructive. I think it's an excellent question. Yeah. Thanks for provoking that digression, Enzo. All right, so I hope we have learned some things, both about sort of like physics of global spacetime structure, and you know, and also some more philosophical themes, like how to even define determinism, and how kind of like physicists these days think of determinism in terms of well-posedness, and how maybe some of the examples of indeterminism that I will look at also in the kind of like last part of this may be sort of fine-tuned, and if they are still fine-tuned or no, that's sort of like in many ways an open question. And it turns out that dark energy figures in it in a kind of non-trivial way. All right. So yeah, as I said, there was almost no dark energy in this so far. But you know, if we seriously think about solving something like Einstein's field equations, then of course they also have this Einstein's horrible blunder lambda term, and as of course you all know, because you're here at the summer school on philosophy for dark energy, there seems to be an the expansion of the universe seems to be accelerating. We have multiple lines of evidence and multiple ways of approaching it. And so I think in this context of the questions of determinism, we should also think about what dark energy means for whether our universe, as seen from a general relativistic perspective, is deterministic or not. I want to talk about two examples where cosmological constant really seems to do some really interesting things. The first is a far future of a universe with positive cosmological constant, and the second will be about interior of black holes if, well, this is not very precise, but like interiors of black holes which have cosmological constant in the exterior. Okay. Wow, that's a funny expectation. It's really something I haven't seen so far. Thank you, past Juliusz, for that embarrassing spelling mistake. Ignoring past Juliusz, let's think about what the expectation could be about what positive cosmological constant means for us. And I think it's a very natural expectation to think that positive cosmological constant enforces certain kinds of convergence to a future state. And the sort of like a heuristic argument for this is that, well, consider some kind of a cosmological spacetime, maybe it's homogeneous, but not exactly anisotropic or something like that. And assume that, you know, insofar as cosmology is concerned, the content of that spacetime is, well, positive cosmological constant, and whatever, a bunch of matter sources. And maybe, let's say that they're kind of like nice. Maybe they satisfy, well, what I mean by this is that they satisfy some energy conditions. In the particular, which of those kind of like depends on the theorem, but typically it's a requirement that all time-like observers will observe positive flow of energy. Now, in that situation, you might expect that for late times, these spacetimes will just necessarily flow towards an isotropic de Sitter-like state. Again, Eric already discussed the de Sitter spacetime a little bit, but just as a brief reminder, it's the kind of like equivalent of Minkowski spacetime, but with positive cosmological constant. So in other words, it's a solution that is maximally symmetric, with as many isometries as we can, but we have this additional curvature term. So this expectation that positive cosmological constant enforces convergence to a particular state is sometimes called cosmic no-hair conjecture. It's called cosmic no-hair with kind of like an analogy of the black hole uniqueness theorems, which state that black holes have no hair, that is, that the kind of like black holes, insofar it's like a single isolated black hole, it's a very simple object, and it's characterized by basically, well, by space-time location that we can ignore, but intrinsically it's characterized just by three parameters: mass, angular momentum, and charge. And if you're thinking about isolated black holes, then unless the source term is really strange, like a classical non-abelian gauge field or something like this, these theorems seem to be true. And so kind of like black hole no-hair theorems establish that the black holes are simple objects, and with analogy with this, the cosmic no-hair conjecture tries to express this idea that under these conditions, the future state of the universe will also be simple. Okay.
Mm-hmm. Yeah, ask it.
Of course.
I understand why you put the conditions that there are some math sources that is in a sense what is the contemporary situation. But I cannot understand why you say that there should be anisotropic. It is a statement, the first statement. Why anisotropic?
I mean, it could also be slightly inhomogeneous as well. Yeah,
The same reason.
for the same reason.
Okay.
Yes. Yeah. Sorry, I should have been more precise.
Okay.
So the idea is that, like, if
There's more anisotropy due to the distribution of matter. Okay.
yeah, or
Because
some
the system
inhomogeneities.
is empty. Okay.
Yeah.
Okay.
But the expectation would be that,
Yes.
like, if I take these anisotropies, then the cosmological constant will kind of wash them away.
It's completely empty.
Yeah,
Okay, sure.
yeah. For the sufficiently late times.
Okay.
Yeah. So it's the same for anisotropies and the same for inhomogeneities, and I should have been more precise. Yeah. Okay. Yeah. So again, a kind of like a version of this statement that's sort of like stated, that's expressed in the terms that we have discussed so far, would be something like this. If I take a class of initial data or initial data sets, which have such that their globally hyperbolic developments are future time-like and or null geodesically complete. So for now, we're ignoring like black hole type space-times, or I guess we're also ignoring like big crunch sort of solutions. So for those developments where which are future complete, so the observers can propagate for as much time as they would like to, as measured, along their world lines. And we pose another assumption that these initial data sets are solutions to the Einstein's field equations with positive cosmological constant, which is, well, it's basically a statement about like the simplest dark energy model that you can think of. The generic elements of that class will be future asymptotically de Sitter. So the conjecture states exactly that. The inhomogeneities and anisotropies will wash away throughout the evolution of the universe. All right. So now we can, I think we're instantly seeing the connection with the question of determinism, right? Because now we want to know, okay, we're here and now, imagine that we are kind of like, I don't know, like maybe we become a highly advanced technological civilization at some point. That's, I guess, unlikely for the human species. But imagine we were, and we were living for a really, really long time. What should we expect the universe around us to be like? Or, maybe not us, but some very, very, very remote descendants of us at kind of like cosmological time scales. All right. So this is the conjecture, and I will not summarize these individual results, and I will not go through a sketch of the proof, because I feel like I've already lost some of you. But what I think you should know about the cosmic know-her conjecture is that, well, it seems to be true. Namely, we can prove it for many, though not all, Bianchi cosmologies. And we can prove it can be proved for a variety of inflationary models. And, for various sort of like systems. So for instance, for the Einstein-Vlasov system, which kind of describes a sort of like relativistic kinetic matter model, it can be done. It can even be done for some situations in holography, so you can kind of like derive it using very general statements about the entropy of the universe having to always increase. You can derive it in the effective field theory framework and in a bunch of other ways. And so under some assumptions, this cosmic know-her conjecture seems to be true, which is good. So now it's a sort of like theorem in general relativity, but what should we think about the theorem? How should we interpret the theorem? And I think it's important to point out that the theorem has some restrictions. There are some things that the theorem does prove and some things it does not prove. And importantly, I think it should be kind of like stressed that this convergence to de Sitter is local, in the following sense that there is nothing like a uniform convergence of the spacetime metric over the Cauchy slice to a homogeneous anisotropic de Sitter metric. It is only if we take a region of fixed physical size that the metric converges uniformly and actually exponentially. It's a nice feature of many of those results that the convergence is exponential. So that gives us sense of a time scale. You can think of this as, oh, once the cosmological constant or dark energy starts to dominate, like it will become dominant kind of like ever faster, which I think is what you should expect if it's really a cosmological constant, right?
What 1983 is the book General Relativity?
No, this is in the paper by Wald. I'm not sure if it's in the book. Maybe. I don't remember if it's in the book, but it's a separate paper, and I have like a list of references at the end of the slides.
Next year.
Yes. Right. Yeah. 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 The book is 1984.
1984.
Yeah. Okay. So what this also implies is that global properties of this cosmological spacetime, say what is the topology of the slice and so on, that does not have to be the same as de Sitter. It's only of the regions of like fixed physical size that the metric converges to de Sitter. And I think it's also important to say that the model does not hold, the theorem is not true for all of the models with cosmological constant, but for a large variety of them. Similarly, it's not true for all inflationary models, insofar as I understand it. But for kind of like large variety of circumstances, the theorem could be derived. Okay, so maybe it's a good moment to like kind of like get kind of like a pictorial intuition for what the theorem establishes, right? So, we can imagine a large variety of cosmologies, and I'll just kind of like super schematically draw like 3 of them. So, here's the first spacetime, second spacetime, and a third one. And we're always assuming that the time will sort of flow upwards. And now we're considering, like the initial data sets that we're looking at, they can be very different, right? Maybe in some of them, nothing very interesting is happening. The initial slice is like nearly flat, and there's not much sort of there. Maybe another one is sort of like, like slightly more curved, and another one of them could be highly varied, like this. And well, what the statement says, what the theorem says is, like if you take, let's say, like a box, like a little space-time volume, V1 in here, and V2 in here, and maybe like a V3 in here, I can instantly see sort of that these volumes, when considered as geometric objects in their own right, like actually as little relativistic spacetimes maybe, right? If we took like a little neighborhood, or like as little pieces of the initial data set, they can be very different. V2 is very different from V3, and so on. But if we evolve it for long enough, then like here, in the far future of the universe are little kind of like V1 for late time, V2 for late time, and V3 for late time. They will be, well, maybe not the same, but if the time is late enough, then for any arbitrary finite kind kind of like precision of measurements, we can find some late time for which there will be basically isometric, basically the same. All right, so that's a theorem. Okay, now what should we make of the theorem? Like how to interpret it? And I think, you know, like a most natural interpretation of the theorem is that it establishes not only determinism, right? It's sort of like assumed in the sense that like, oh, we took those initial data sets that have kind of like nice enough future developments. But I think it also establishes something stronger. It establishes that not only the future of these models or the future of subregions in those models, I should say more precisely, right? Because globally, these things can be different. But the future of subregions in those models is not only determined, but it's unavoidable. No matter what we would have, what kind of intervention we would have done, you know, like maybe we're here in this situation. We're kind of like imagining a cosmically advanced civilization that can like genuinely like do something around us, and we're like, oh, maybe if we flatten things a little bit, then in one direction, then maybe we would avoid this state. Or maybe if we kind of like make things a bit more curved, you know, like an intervention that sort of takes us in like more like this or more like this, maybe we could avoid our far future being this kind of like dark energy dominated void. And I think the natural interpretation of the theorem is that this is not really possible, at least for very large regions of parameter space. This is not possible. Small changes to the initial data set cannot take us away from this asymptotically de Sitter state far enough into the future. I mean, of course, like I stated this as if this was an existential concern for us, and of course it's not. We will not enter into the dark energy dominated stage of the universe for a really, really long time. But, you know, if we want to think seriously about what the far future of a universe is like, and we assume that it has positive cosmological constant, and those other kind of like assumptions of the theorems are true, this is what we should expect. And I think as philosophers, we should kind of think about what we should expect from the far future of our universe. And if dark energy is, well, since dark energy seems to be a feature of our universe, then I think we should say that if dark energy is either positive cosmological constant or one of those inflationary models, or, you know, for some models of the dark energy, this is the expectation that we should have. So from this point of view, our universe, our future of our universe is not only determined, is unavoidable. And I think it's sort of like, you know, like important to distinguish this from like a usual situation that we're dealing with determinism, right? Like, you know, like if we have like a, I don't know, like a bunch of like point particles in a Newtonian universe or something like this, like maybe, you know, maybe we could, of course, I'd assume now that this is none of those like funky Newtonian systems that I have mentioned, no Norton's dome, no nothing, right? It's just like a bunch of particles and the problem is well posed. Like, you know, like maybe some of them will collide, maybe none of them will collide, maybe all of them will collide. And kind of like by manipulating or you know, like the nature, sort of like by introducing like random fluctuations could take us, you know, maybe from this solution to that solution or this solution to that solution. And their qualitative behavior in the far future could be very different in principle. But, and those, of course, would be all deterministic systems, but they wouldn't have this feature of unavoidability of fatalism. And so I think this is one of those things that, at least it seems plausible, that dark energy does to our universe, or at least to kind of like any finite-sized box of our universe. And so from this point of view, we do get, I think, an interesting question as to, you know, what assuming that dark energy is real and assuming central models of dark energy, what should we expect? What kind of answers to the issue of determinism we do get? So I think it's both physically and philosophically non-trivial, I guess. All right. There are, of course, some caveats because the world is never as clear and clean. The first is something I have already said. Not all models of dark energy do that. Even some models with positive cosmological constant don't display this behavior. Many of them do, but not all of them do. So we could naturally ask ourselves, how much of this is true for other models of the dark sector? And I think it's an excellent question. Thank you, Juliusz, for stating it, and I have no idea what the answer is. Go ahead. Oh, just a moment. It's Mart over there.
No, it's just a clarificatory question. You say like not all the models do that because you say it's a theorem that has been proved just for some models.
Right. Yeah, for some symmetry classes and perturbations of those symmetry classes. Yeah.
Okay, but I mean, for those ones, looks like the fatalism interpretation is it's the only one, or it's.
That's an excellent question.
Okay.
And you're kind of like a step ahead of me in the slides. So that is an excellent question, right? Because now you could kind of like introduce yourself into this kind of like frame or state of mind where you're like, well, okay, like we were only looking at cosmology, but there's like, of course, a lot of other physics here, right? Like there's maybe non-trivial matter content, or maybe, like we have collapse to black holes, or, all sorts of things will happen, right? And so at cosmological scales, the statement of fatalism is kind of like, no matter how big of a box I would take, I would end up in the Sitter state. But now, again, kind of like going back to this like fairy tale of a highly advanced civilization, like, it's like a very, very poor and underdeveloped science fiction. Could we avoid convergence to the Sitter for some interesting little volume? And well, already Bob Wald in 1983 says that like the theorem that he considers ignores a lot of things, including black hole formation, right? Like a more realistic picture of this would be, oh, like somewhere near here we will have, like, I don't know, like collapsing stars and things like this. And so if I'm kind of like, here's my like little star, then that should collapse to a, I don't know how to draw it, maybe this is the star, and so it should kind of like collapse to a black hole, which for some reason ends up being like a red hole on this. And like this, if this is now the region that I have been looking at, I should not expect it to end up in the Sitter state. I should rather expect that the far future will be the Sitter with a bunch of black holes. Yeah. And so that, you could also ask this sort of like similar question about, oh, maybe we thought a lot about black hole thermodynamics, and well, yes, this is a black hole that forms, but then it will begin to evaporate, right? And so then, I guess the question as to like what you should expect the very far future state of this region to be kind of like seems to depend on what you think about this process. Like, does it end with some kind of like a non-singular transition? Then, if so, then I guess it would be like, like some quantum gravity magic happens kind of over here at the late stages of the evaporation. But then, like the evaporating black holes, I don't know, I guess a non-singular transition to something else. And if so, then I would expect that to kind of like effectively become a classical system later on, and also its region of support would be kind of like washed away. But maybe, you could think that like some other option is viable. Maybe black holes don't evaporate completely, but turn into stable remnants or something like this. Then I guess you would have a bunch of remnants in here. Or maybe, maybe the black hole evaporation ends with transition to a naked singularity, and then we're like losing any control over that whatsoever. And like if this ends up with a naked singularity, then who knows what its causal future will be like. All sorts of crazy things, like old socks and Trump's speeches, to paraphrase John Ehrman's phrase, could come out of a naked singularity, and we're kind of like losing control over that. And so then this sort of question as to what you should expect the future of a finite box with a black hole or with a star collapse into a black hole would be, in principle, like if we kind of like switch on this other physics, would also depend on these kinds of issues. Yeah. Yeah, which is just what I wanted to have on the slide, actually. Yeah. So yeah, I think it's an important caveat that again, for some regions of the universe may kind of like avoid this fatalism by, let's say, collapse into a black hole. But then, is it a good escape? That sort of depends on what you think interior structure of black holes is like. If you think that those generically have unavoidable singularities that we would be crushed in, then it's not a very fortunate way of escaping fatalism, I think. But maybe something more interesting happens in the interiors of black holes, and actually it turns out that dark energy has say about it. So, which will be like the subject of the very last part of this. But I think it's also important to stress that this is a very kind of like there's a lot of sort of like physics missing here. Like first of all, like all of the kind of like large scale structure, galaxy formation, black hole feedback, all of this is like not present in the picture, and I don't think it would change that much, but who knows? And like, there's a lot of background assumptions here as well. Like, yeah. I think we're really, there's this excellent question that I have no idea how to answer. Like, should I expect convergence to de Sitter for kind of like variety of other models of dark energy, especially if it's like a complicated dark sector? I think it's, if one of you like knows or has an expectation, then please tell me. I know that I can prove the theorem for some inflationary models, but I don't know, there's so many inflationary models. I don't know what should be my generic expectation about the like asymptotics of those models. But at least, insofar as classical GR is concerned, that I think is what we should expect, modulo all of the craziness that happens in black holes. Yeah, so I guess I should talk about some of the craziness that happens in black holes. And I will be drawing more pictures. So let me just like take a photo of this, just like in case we also want to put this sort of so that someone who watches the recording of the talk has ideas what happened. Oh yeah, the camera I guess already took it much better than my phone. Awesome. All right.
Philosophically speaking, you are arguing that there is no one more argument that there is no free will in our universe.
That's a good question.
It's philosophical.
Do I have a view on this? No, I think this is like perfectly compatible. So I had this picture, right, with like, oh, here's a box and maybe we as highly advanced civilization, we can do something. I think, you know, like we might have like a free will in this kind of like limited sense. Oh, like maybe, you know, maybe, I don't know, we will collapse. Well, we cannot really collapse our sun to a black hole, I guess. It's too small. Maybe, you know, maybe we go around, collect a lot of matter, throw it into the sun, it collapses into a black hole. Like, that is something that we might be able to do, all sorts of like freedom to do interventions, which would be just kind of like small perturbations of the initial state. I think at large scales, the right thing would be to say is that our interventions cannot matter in these kinds of cosmologies. But it's kind of like compatible with, you know, both we cannot change anything in the initial data set, or we could change things a little in the initial data set, and kind of like short term it could change a lot, but long term it wouldn't matter. I think that would be like a better thing to say. So yeah, if you want to phrase it as, could we have a delusion of grandeur and change anything on cosmological scale in these cosmologies? I guess we can't, apart from, you know, like maybe we could throw ourselves into a black hole or not, right? Or like something like this.
Black holes, did you investigate also the case, one is space itself is self-emergent?
No, I haven't thought about these cases. I don't know. Like I don't. Yes, right. So I think this is why it's a great question. What happens if we have more complicated dark sectors? Should I expect the same behavior or not? And I just don't know what the answer is.
No, you will not expect. Because it will be changed from it itself.
Yeah. I mean, I guess I could also, you know, like I don't know how to motivate it physically, but I could imagine a sort of like time varying, like maybe it's a cosmological, maybe it's like a scalar, dark energy is like a scalar field, but it's not really a constant, it's a time varying or time dependent, and I guess at some point it could just switch off, right? I don't know how to motivate this sort of speculation physically, but if it would just switch off, then of course this sort of situation would not arise, and we would end up with very different asymptotics. So I guess that's like, this is one of the ways in which I can kind of like convince myself with like a very silly toy model that this expectation really sensitively depends on the physics of dark energy, which I think makes it an even better philosophical subject for philosophical investigations. All right. So what if there are black holes? Let's go back to what I have discussed in the first part, namely the you know, global hyperbolic developments and Cauchy horizons. And I want to talk about this because it's sort of like if we think about black holes in high symmetry, we, in accordance with the black hole no-hair theorems, we basically have three options, right? We have, I will only draw like portions of the Penrose diagrams, and again, like, Eric talked about Penrose diagrams yesterday, so I will not, but feel free to ask me, you know, if you need any clarification. So sort of, what could black holes look like? Again, just classically. Well, maybe it's a spherically symmetric, I guess it's really like a static solution. We could have like a non-stationary version of this, but that wouldn't change the diagram in essential ways. So it could be Schwarzschild-like. So how to interpret this kind of a diagram? Well, this is the scribe plus, so all of the kind of like null curves that's remain in the exterior travel there. The exterior is asymptotically flat, and this will be very, very important in just a moment. And here we have the surface event horizon that sort of separates the region from which a signal could be sent to scribe plus from a region of no return inside the black hole. Okay. Now, black hole could, of course, be more complicated, right? Maybe it's the Reissner-Nordstrom or Kerr black hole. So if it's a Reissner-Nordstrom, then it would look a bit different. It turns out that it would look like this. It would have a more complicated interior structure, and the structure would be kind of like the following. Again, in this diagram, we can also kind of like glue some things over here and glue some things over here. It's really like a portion of the full GR spacetime, but let's ignore it. And we're just imagining the situation where, you know, like similarly to the Schwarzschild, here we are in the exterior, everything is asymptotically flat. Here's our scribe class. But it turns out, and we know this from kind of like explicitly investigating the solution, that the interior of charged black holes is very different from the interior of non-charged black holes. And in particular, it has a sort of like a singularity that kind of like acts as a source of the charge. And apart from having a single like a single horizon, the event horizon, in the interior, kind of like, you can think of this as getting close enough to the charge source, I guess, there would be a second horizon. And this turns out to be a Cauchy horizon in the sense I have described earlier. So if we, you know, here we can imagine like a collapsing star to the black hole, and, you know, we can kind of do this as a sort of like toy version of a dynamical problem. If we did the same sort of for a collapsing star in here, the development of those initial data set for you know, like a star with large with non-negligible charge would develop a Cauchy horizon, and we don't really know what would the interior look like. Like in these diagrams, we typically specify a particular interior, but there's a bit of technical magic that goes into this. There are analyticity assumptions, and if you can relax those, then interior past the Cauchy horizon could basically be anything. So the takeaway from this is that the Reissner-Nordstrom black holes are an example of indeterminism. And it's even worse in the case of Kerr black holes, because the corresponding diagram for a Kerr black hole would look like this. Again, here is the exterior, here's the event horizon, scribe class, and if you kind of like trust the analytic, there's like a unique analytic extension and plenty of non-analytic extensions, and even in the analytic extension, the interior of this is very, very unusual. For instance, the analytic extension, this is something you cannot see from this diagram, has closed time-like curves, just in the sense that I kind of started this talk with. And this is, I think it's, of course, it's like physically significant, but it's also philosophically interesting. Because, well, this is sort of like a first order, zeroth order approximation, if you wish. This is, well, we do believe that kind of like black holes have net zero charge on some sort of more or less hand-wavy astrophysical grounds. Namely, like if there would be like a large imbalance, then kind of like things would sort of like equalize. So we're not very concerned about this as to what the real world is like. But we do have pretty good reasons to think that every single black hole in our universe is Kerr-like. It's a rotating black hole described by the Kerr solution. But Kerr solution has this complicated interior structure. So does it mean that determinism, for instance, fails in our universe because Kerr has a Cauchy horizon on the inside? Does it mean that time travel is possible in our universe? Another feature is, oh, that's maybe something I should also mention for the kind of like those of you who studied logic. There's a class of spacetimes, sometimes called Malam and Hogarth spacetimes, which have this fascinating property that there exists a future, a causal curve which is infinite, and it's entirely contained in the causal past of a single point. And Kerr solution has that property, and what you can do, and what some logicians and philosophers contemplated, would be putting a computer on this infinite curve. I can actually draw it. This is our curve, and this is sort of a point such that this curve will be fully contained in the past of this point. So we can imagine, like taking a classical computer, putting it on this curve, it will have infinite time to do the computation. So just set it some interesting task, like maybe tell me if Peano arithmetics is consistent or not. Whereas we ourselves kind of like jump into the black hole, and we only have to wait a finite amount of time to get an answer. So you can contemplate these sorts of scenarios, and I think it's quite remarkable that they actually do not only arise in those cut and paste artificial models of GR, but also in something as physically sensible as the rotating black hole solution of GR. Okay, but, well, so we're kind of here. Many highly symmetric, and so in this sense, standard black hole spacetimes have Cauchy horizons. But you could say, if you were, you could say at this moment, Juliusz, but this is super confusing. Like, how does that make sense? Like, you waved your hands at all this strong cosmic censorship business, and that seems to be incompatible with that, right? Well, it is incompatible if the strong cosmic censorship conjectures are true. So if the conjectures are true, then kind of like, yes, maybe it's a feature of the highly symmetric Kerr solution, but if we waved or wiggled it a little bit, then this feature should be lost, and this should be replaced with a singularity not that different from the Schwarzschild spacetime, and determinism would be restored, and I guess logicians who want to know about Peano arithmetics would not be so willing to travel to insides of black holes, if you will. Okay, what all of this has to do with dark energy? At this stage, not much, but in 1979, Roger Penrose proposed the kind of like heuristic for thinking about what happens at this surface and what happens at this surface. And the heuristics is basically a kind of like infinite blue shift argument, and since then the argument has been kind of like spelled out in more details and also explicitly calculated for a variety of black hole solutions. So the idea is that, well, here, wait, I think I have blue here even. That's great. The idea is that here, like, imagine you're an observer who wants to sort of like jump into the deep interior of a Kerr black hole. There will be all sorts of, like we can imagine all sorts of signals coming in from the outside, but due to the causal structure of this whole situation, these signals can build up to arbitrarily high frequency. And if you then sort of like wiggle them a little bit, then maybe something like transverse derivatives of those waves would blow up. And if that would be the case, then the infinite blue shift, if this signal started to sort of like blow up and you back reacted it on the spacetime, then this whole situation from being a kind of like surface that an observer can travel through would turn into a form of singularity. Sometimes this is called a weak null singularity. It's weak because the analysis is sort of like somewhat perturbative, and it's null because, well, this is like a null line in the spacetime. Okay, so these heuristics can be used to sort of kind of prove a version of the strong cosmic censorship for this space-time, right? It's sort of like, oh, if we neglect this aspect, then we think of this as just the highly symmetric solution, then sure, maybe you can travel to the deep interior, but in a more kind of like realistic, perturb or generic situation, you should expect all of these signals coming in from the exterior, and that should prevent me from traveling further. And if so, that would be great because it restores the uniqueness of the solutions to the Einstein's field equations in here, in a generic situation. In other words, the Cauchy horizon of Kerr is just like an artifact of idealization. Now, all of this heuristics is kind of like carried out in the context of asymptotically flat spacetime, and this is where dark energy will become relevant in just a moment. Oh, this is just a digression that I kind of. No, I think I have to. I don't have time for this digression. Turns out that a very weak or very strong, if you will, depending how you look at it, version of cosmic censorship seems to be already false in the Kerr case. So there are C0, so midly continuous, but not continuously differentiable, or not even like twice differentiable extensions for generic initial data sets if certain other statements about the Kerr are true. Anyway, this is a digression. But now, what all of this has to do with dark energy? Well, it has to do with dark energy insofar as instead of contemplating this kind of model, you could contemplate a slightly different one, namely the situation in which we have our Reitsner-Nordstrom type black hole, but the exterior of it is, sorry, this should be like a squiggly line to kind of like indicate the singularity. Now the exterior of this is no longer asymptotically flat. The structure of the infinity is different, and the asymptote here is now the de Sitter spacetime. So now, if you think of this infinite blue shift heuristics and you change the asymptotics to de Sitter, which is what we should do, right? Like if it's, like a charged black hole in our universe and we kind of like live long enough, or we're interested in what happens to it very, very far in the future, kind of per cosmic no-herference, like this is the asymptotics we should look at. In other words, this is the asymptotics we should look at if we want to know what happens to black hole interiors at late times, so to speak. And now you immediately notice that, oh, okay, like I had this argument that signals here kind of like piling on the Cauchy horizon would be infinitely blue shifted, but now I do have a competing physical effect, namely cosmological redshift, right? The signals should become kind of like weaker and weaker as the expansion continues. And so in particular, if so, then they should not pile to arbitrarily high frequency, and this way of kind of like turning this into a weak-null singularity just doesn't seem to work. And because I'm slowly running out of time, I would just say that there are both numerical, there are numerical models which seem to establish that for some parameter ranges, so for high masses and high charges, this indeed seems to be true for Reitsner-Nordstrom black holes. And this can be also kind of like computed for some particular matter perturbations. And so what is a philosophical upshot of all of this highly technical mathematical relativity nonsense? I think the philosophical upshot is that dark energy might, in some situations, lead to violation of strong cosmic censorship. And therefore, it really matters for the question of determinism whether we live in a universe with positive cosmological constant or not. Because the answer changes. Like some kinds of arguments that seem to work pretty well, if it's like an isolated black hole and there's nothing else in the universe, stop to work if, at least classically, if our universe becomes dominated by cosmological constant for late times. And I should have said that, of course, this was all kind of like classical. More could be said. In particular, there is a kind of like quantum field theory in curved spacetime argument that even though classically we can kind of like compensate for the blue shift, there are still other sort of physical effects, and that restores uniqueness, but that takes us kind of like too far away from this. But you should know that like it's not so simple as to say, oh, like determinism fails. Maybe if we switch on yet another physical effect, like something about semi-classical gravity, then we do restore the uniqueness, or we kind of like save determinism after all. So it's a sort of like, I think it's an interesting game, and I think it's very much worthy of attention of philosophers of physics, like what's going on in these cases. Yeah, these are just like some philosophical questions that I think arise. So and I think some philosophers do have very strong opinions or commitments to determinism, but like, should we even be concerned if, I don't know, like classically determinism fails on the black hole interior for very, very far away in the future of the universe? I mean, I don't know, I guess if you're one of those people, tell me. And like, what even make of violations of determinism in those situations? Kind of like a more GR question would be, I haven't talked about this explicitly, but in these sorts of situations, perturbations of black holes, very often we don't get smooth extensions, but only like C2 or just continuous. So what is even the physical significance of this? Of course, it's interesting mathematically, but what should we think about it physically? And yeah, what are the standards of stability used there? Does this happen in other models of dark energy as well? Again, Juliusz, thank you for asking that excellent question that I have no idea how to answer. And yeah, with this, I think I'm almost ready to wrap this up. So just a brief summary. You were interested in the question of, like, is GR deterministic, and is our universe as seen by GR with dark energy, for the simplest cases of lambda really being like a constant, true? And well, with some caveats, we have this form of fatalism about the future of sort of like finite pieces of the universe. But for black hole spacetimes, positive lambda, at least classically, makes the universe less deterministic. But of course, determinism is not the same as prediction, right? We do not have observational access to anything like a Cauchy surface of our universe, even if our universe has a Cauchy surface. At best, we can access a tiny part of that surface. So what could we even know about global structure of our spacetime? And in particular, is in the universe with positive cosmological constant, would our epistemic situation be better or worse, or maybe the same as if lambda had been equal to 0? And I think that's just a perfect topic for Thursday afternoon. Thank you.